All right, folks, our next topic is determining the area between curves and applications. So, area between curves, here are the objectives we're going to look at in this section. The area, how to determine the area between two curves. Apply the area between two curves to an application where we'll look at tree growth. Determine the area that's bounded by two curves. And then we're going to apply the area bounded by two curves to an application where we find total profit. So let's look at this introductory example to try to figure out what's happening here. So we're going to write a definite integral for each of the shaded regions for the given figure, and we're going to write an equation that relates these definite integrals. So here's the first figure. We're going to write a definite integral for that shaded region. Notice that shaded region is the region below the graph of f, above the x-axis, between x equals a and x equals b. We're going to write a definite integral for that shaded region. Notice that shaded region is below the graph of g, above the x-axis, between x equals a and x equals b. And then we're going to write a definite integral to find the shaded region shown in the third figure. And notice that shaded region is the region that is between the curves given by f and g, and between x equals a and x equals b. So we know for the first region, the area that's below the graph of f, above the x-axis, between x equals a and x equals b, is given by the definite integral from a to b f of x dx. Likewise, the shaded region that's below the graph of g, above the x-axis, between x equals a and x equals b, is given by the definite integral from a to b g of x dx. So the shaded region in the third figure that's between the two graphs, intuitively it should be nothing more than the area that's below the graph of f minus the area that's below the graph of g. And I would write that as, well, the area below f, that's the integral from a to b f of x dx. The area below g, well, that's the integral from a to b g of x dx. So subtract those two areas, and we could write that as one definite integral using a property of integrals that define the area of the region that's between the graphs of f and g. We'd integrate from a to b f of x minus g of x dx. So that's how we find the area between two curves. Let me write this down like in a definition. Area between two curves. So on a closed interval AB, the area between two continuous functions f and g is given by, well, this mess. So notice, that's two different cases. Well, what if function f is above function g on the interval? Then we integrate from a to b f of x minus g of x dx. And then the second figure is like, well, what if function g is above function f? Well, then we would integrate from a to b g of x minus f of x dx. There's another way to remember this, rather than thinking of it as two different separate formulas or processes that you have to go through. Here is the much simpler way to remember it. And it doesn't matter what the functions are called. F, g, h, they could both be called y. The area between two curves is given by integrating from a to b the top curve minus the bottom curve. So it doesn't matter what the top curve is called, f, g, h, or y. It doesn't matter what the bottom curve is called, f, g, h, or y. You just integrate the top curve minus the bottom curve. So why don't we look at an example? Let's determine the area that's between the graph of f of x equals negative x squared minus 3x and g of x equals 4x plus 12. And we're going to look on the interval negative 2 to 3. So the first thing that we need to do, you can't do one of these problems without looking at the graph. How do you know what's the top curve? How do you know what's the bottom curve without looking at the graph? So I'm going to put the graph on the board, but before I do that, I want to get the graph here real quick. So here's my calculator. So in y1, I'm going to put function f. So function f is negative x squared minus 3x. Then in y2, I'm going to put function g, which is 4x plus 12. And you know what? It says I'm looking on the interval negative 2 to 3. So I'm going to make my viewing window. I'm going to make my x min negative 2. And I'm going to make my x max 3. I'll go ahead and scale by ones. Y min and y max, gee, I really don't know. So let me just start off by saying, I'm going to make my y min, let's make it negative 10. And I'm going to make my y max positive 10. Let's see if I can see what's happening here. So here I'll go. I'll make the graph. Well, it looks like part of the graph is off the screen here. So let me just come over here and fix my y max. 10 wasn't quite large enough. So you know what? I'll go to 30 now. And I'm going to change my scaling on my y-axis to be 4s. All right. Well, you know what? This is coming off the screen down this way, so maybe I could go adjust the viewing window, but I think I have enough. I see what's happening here. The red graph is above the blue graph, so keep in mind the blue graph was function f, the red graph was the line 4x plus 12. So I see the top curve is 4x plus 12, and the bottom curve is negative x squared minus 3x. So I have the graph, I see the graph, so I'm going to put the graph on the chalkboard, and I'm going to head off to the chalkboard now to work through this example. All right, in this example, we're asked to find the area between f of x equals negative x squared plus 3x, and g of x equals 4x plus 12 on the interval negative 2 to 3. So, the first thing you have to do is to look at the graph. So I looked at the graph, and this is what the graph looked like. But I went ahead and I just kind of shaded what it is we're trying to find the area of. It's the area that's between these two graphs. Well, just in looking, the key is to find the area between two curves. You're going to integrate the top curve minus the bottom curve. So that means here I want to integrate the top curve, 4x plus 12, minus the bottom curve, which is negative x squared plus 3x. And my limits of integration, sorry, I have a typo here, a typo on the board. This function was x squared minus 3x. X squared minus 3x. You probably saw my typo, but I wanted to catch it quickly. So now my limits of integration, well, it's the interval negative 2 to 3. I'm looking at what's bounding left and right this region, negative 2 and 3. So my limits of integration are negative 2 to 3. Okay, what I would do is I would clean up my integrand. I'd distribute the negative 1. I would combine any like terms. And if I do that, I get, I've got a negative sign there, x squared. Let's see, 4x minus negative 3x, that's 7x. Well, then just plus 12. So that's what I'm trying to integrate. Get an antiderivative. Let's see, we have 1/3 x cubed plus, see, the antiderivative here is 7/2 x squared. The antiderivative of 12 is 12x. And we need to evaluate that from -2 to 3. So you have to use your fundamental theorem of calculus to evaluate it. Remember, the 3 goes in first for the x's, minus, then you put the -2 in for the x's. And if you do this correctly, you should get 535 over 6, or as a decimal, that's 89.16 repeating. I mean, I personally would probably just go with 535 over 6 because this is not an application. So that's what the area is between those two curves. So to practice this, I want you to pause the video and do exercise number 21 here in section 7.2. So pause the video, go do exercise 21. Once you finish exercise 21, you know the drill. Restart the video and I'll be here at the chalkboard working through the solution. 21, you were asked to find the area between f of x equals x minus 3 and g of x equals x squared plus x plus 1 on the interval -2 to 1. So again, the first thing you have to do is look at the graphs. How can you find the area if you don't see what the region is you're trying to find the area for? And the only way to do that is to make a graph. So when I made the graph, I used my calculator to get the graph, and then I wrote down on the board here what the graph looks like. Here's the x squared plus x plus 1. Here's the x minus 3. So this is the region I'm trying to find the area for. So remember, to find the area, I'm integrating top curve. Well, the top curve is x squared plus x plus 1 minus the bottom curve. And the bottom curve is x minus 3. And I'm finding that area on the interval -2 to 1. And then, just like I did in the example, I would clean up my integrand first. It just makes the calculus easier. So I have an x squared. See, x minus x, well, that's 0. 1 minus -3 is 4. Get an antiderivative, which is 1/3 x cubed plus a 4x. Evaluate that from -2 to 1. You evaluate it from -2 to 1 using the fundamental theorem of calculus. So the 1 goes in for the x's first, minus the -2 going in for the x's, and you end up with the area being 15, or technically 15 square units. But that's all there was to number 21. Hopefully you're seeing this isn't bad at all. So let's head on back to the slides and see what's next. All right, after working through that example and doing number 21, hopefully you see this isn't too bad. So let's look at an application. So from in this example, from past records, a botanist knows that a certain species of tree grows at a rate of 3/2 x to the -1/2 feet per year. X is the age of the tree in years. However, if a special nitrogen-rich nutrient is given to the tree, it grows at a rate of 2x to the -1/2 feet per year. So on the interval 1 to 4, how many more feet in growth would result from this special nitrogen-rich nutrient? So think about this. We're given two rate functions here. The first rate function, 3/2 x to the -1/2. And the second rate function is 2x to the -1/2. And that 2x to the -1/2 is if they give it a special nitrogen-rich nutrient. So to determine how many more feet, how many total feet in growth is going to be the result from the special nitrogen-rich nutrient, it looks like we're going to be integrating a rate function on the interval 1 to 4. So let me, again, let me call up my calculator so I can see a graph of what's happening here. So let's see, and y1, I'll put, well, let me clear that out. I'm going to put the 3/2 x to the negative 1/2. So I'm going to put this function in y1. So 3/2, okay, that's 1.5. X to the negative 1/2. And then in y2, I'm going to put the function that has the models with the special nitrogen-rich nutrient, and that's 2x to the negative 1/2. And let's see, my viewing window. Let me pull this over here. So I'm looking on the interval 1 to 4. So I think that would be from year 1 to year 4. So let me come here and let me make my x min 1, my x max 4. Let's see. So the y's are going to be telling me something about feet. So I think a y value of 0 would be a good min. Y max, I don't know. I'm going to go with 5 just to see what happens. So here comes the graphs of those two rate functions. Okay, so keep in mind the blue one, that was the 3/2 x to the negative 1/2. The red graph is the 2x to the negative 1/2. So it looks like I need to integrate top curve minus bottom curve in order to determine how many more feet in growth would result from the special nitrogen-rich nutrient. So I'm going to head off to the chalkboard. I'm going to work through this example so you know the drill. But I'm going to put, first thing I'm going to do is have this graph on the chalkboard. All right, this was an application of area between two curves. So hopefully you wrote down, in your notes, what the example was, all the words there. So in short, you were given two growth rates for a tree. This growth rate, 3/2 x to the negative 1/2, was without any special nutrient. This 2x to the negative 1/2 was if the tree received a special nitrogen-rich nutrient. And so we were asked that on the interval 1 to 4, now keep in mind 1 to 4, x was the number of years, so that'd be like 1 to 4 years. How many more feet results from the special nitrogen-rich nutrient? Well, that is area between two curves here. Remember, we're given rate functions. When you integrate a rate function, it gives you a total, some total accumulation. So here the area between the two curves is giving us the total. How many more total feet did the tree grow because of the special nitrogen-rich nutrient? So just area between two curves. We have to integrate. The top curve minus the bottom curve. Well, the top curve is 2x to the negative 1/2. The bottom curve is 3/2 x to the negative 1/2. On the interval 1 to 4, and I'm going to clean up that integrand before I start to do any calculus, and this cleans up nicely. These are like terms. So 2x to the negative 1/2 minus 3/2 x to the negative 1/2. Well, let's see, 2 is 4/2. So I just get a 1/2 x to the negative 1/2. Which the antiderivative of that, how friendly is this? It's just x to the 1/2. And the fundamental theorem of calculus quickly gives us 4 to the 1/2 minus 1 to the 1/2, which square root of 4 minus square root 1. Square root of 4 is 2. Square root of 1 is 1. 2 minus 1 is 1. So what this tells us is that I'll write this out, from year 1 to year 4, year 1 to year 4, the special nitrogen nutrient, the special nitrogen-rich nutrient, what it did was it resulted in an additional 1 foot of growth. And that was it for this example. So let's head on back to the slides and see what's next. All right, so doing that application, we saw that the special nitrogen-rich nutrient produced about an additional 1 foot of growth for the tree. So the next task is to determine the area that's bounded by 2 curves. So we're going to determine the area that's bounded by the curves y equals negative x minus 3 and y equals 9 minus x squared. So again, first thing you have to do, you have to graph each function. You have to see what it is you're trying to find the area of. So let me call up my calculator again. And let's see, I'll clear that out. So in y1, I'll put the negative x minus 3. And in y2, I'll put the 9 minus x squared. Let's see, viewing window. I'm just going to start off on the x-axis going from negative 5 to 5. Y-axis, I'm going to start off going, negative 10 to 10. And let's see what the graph looks like. All right, so I see the blue line, that's the y equals negative x minus 3. The red parabola, that's the 9 minus x squared. So I see the region that I'm trying to find the area of, but I don't know my limits of integration. So what I have to do is I have to find the points of intersection, where these 2 graphs intersect. So since I have my calculator up, let me show you how to do this on the calculator. So that's second trace, and it's number 5, intersect. And I just have to move the cursor close to the point of intersection. That's pretty close. So I hit enter, enter, enter. Okay, it tells me that point of intersection is negative 3, 0. I would label that on my graph. And you know what? Let me find, I could have just scrolled over here. Let me find this point of intersection. That looks pretty close. Enter, enter, enter. And it tells me that point of intersection is 4, negative 7. So I'm going to head off to the chalkboard. I'm going to have this graph on the chalkboard. I'm going to have those points of intersection labeled. And then when I get to the chalkboard, I'm going to show you how to algebraically determine the points of intersection. So let's head off to the chalkboard and finish off this example. All right, folks, in this one we're asked to find the area that's bounded by the curves y equals negative x minus 3 and y equals 9 minus x squared. And so remember, the first thing we do is graph, and I graphed it. I showed you the graph on the slide, and I showed you how to use the intersect command to find the points of intersection, because we need to know where these curves intersect so we can find the area of the shaded region. And I also said I would show you how to find these algebraically. And we need to remember how to find it algebraically in case when we use the intersect command we don't get nice friendly numbers. I mean, -3, 0, that's a friendly point. 4, -7, those are friendly numbers. So remember, to find where two curves intersect, you want to know where they are equal to each other. Intersect is where they are equal to each other. So you would take -x minus 3 and set it equal to 9 minus x squared. You want to know where this curve is equal to this curve, where they are equal. Now I would add x squared to both sides. And subtract 9 from both sides. So -3 minus 9 is a -12. This factors to x minus 4 times x plus 3. Set each factor equal to 0, and you get x is 4 or x is -3, which we see that here, and we saw that on when we used the intersect command. And I just only need to know, for the problems we're going to see, I just need to know the x-coordinate of the point of intersection. So now that I know, and I've reviewed algebraically how to do it, you find the area the same way. You integrate the top curve. The top curve is 9 minus x squared minus the bottom curve, which is -x minus 3. And we're integrating on the interval from -3 to 4. And again, I start off by cleaning up my integrand here. So I have a -x squared, let's see, plus x plus 12. Get my antiderivative, which is -1/3 x cubed plus a 1/2 x squared plus a 12x. And then I use my fundamental theorem of calculus, and I end up getting 343 over 6, or 57.16, where the 6's repeat. So sometimes you're not given the interval, you have to graph, you have to find the points of intersection, kind of setting up what's going to happen in the next section. I mean, the next section, section 7.3, it is nothing but two specific economic applications of area between curves: consumer surplus and producer's surplus. So it's kind of a friendly section. It's the same concept as what we're doing in this section. It's just applied to producer surplus and consumer surplus. But before we get to that next section, let's head on back to the slides and see what's left here in section 7.2. All right, so we saw how to find the area that's between two curves. Continuing on, folks, we know that marginal profit is a rate function. So if we want to determine the total profit for some item on an interval, and I'm just arbitrarily making an interval, say x equals 0 to x equals 35 units sold, to find that total profit, we would simply integrate from 0 to 35 the marginal profit function. Remember, when you integrate a rate function like marginal profit, it gives a total. Now here are some things we know. We know profit is revenue minus cost. P of x equals R of x minus C of x. If we differentiate both sides of that equation, P of x equals R of x minus C of x, we get marginal profit equals marginal revenue minus marginal cost. Remember, the derivative of profit is marginal profit. Derivative of revenue is marginal revenue, and derivative of cost is marginal cost. So that means that if we wanted to integrate from 0 to 35 marginal profit, well, marginal profit's the same thing as marginal revenue minus marginal cost. So integrating from 0 to 35 MP of x dx is the exact same thing as integrating from 0 to 35 mr of x minus mc of x dx. One more item. In Chapter 5, we saw that profit is maximized when marginal profit equals 0. Well, if in this equation right here, you take marginal profit, you put 0 in for marginal profit, you see marginal profit is 0 exactly when marginal revenue equals marginal cost. These are just some little facts that might help us going forward. So let's look at this example. So T42 makes high-end tea products. One of their best sellers, the Mocha Mint, has a marginal revenue given by the function r prime of x equals negative 1.7x plus 130, and a marginal cost given by c prime of x equals 2.3x plus 14. And here x is the number of boxes of Mocha Mint tea in hundreds. And both of those marginals are given in dollars per unit. Knowing that profit is maximized when marginal revenue equals marginal cost, just reiterating what I just said on the previous slide, let's compute the total profit from x equals 0 to the value of x where r prime equals c prime, where marginal revenue equals marginal cost. Where marginal revenue equals marginal cost, well, that would be where profit is maximized. So write this example down. You know the drill, because I am heading off to the board to do the example. Hey folks, in this example, it was an application, and we were given the marginal revenue function and marginal cost function for a company that makes Mocha Mint tea. And we're being asked to find the total profit from x equals 0 to where profit is maximized. Now it said in the example, compute the total profit from x equals 0 to the value of x where marginal revenue equals marginal cost. But where marginal revenue is equal to marginal cost, that's where profit is maximized. So the first thing I need to do, I need to determine what value of x profit is maximized. In other words, I need to determine where does marginal revenue equal marginal cost. Well, marginal revenue is negative 1.7x plus 130. Marginal cost is 2.3x plus 14. And let's see, I'd add 1.7x to both sides, subtract 14 from both sides, and then divide by 4. I get x equals 29. So I know profit is maximized at x equals 29. I want to compute the total profit from x equals 0 to the value of x where profit is maximized. So keep in mind, this is just an application of area between curves. I mean, we're still integrating top curve minus bottom curve, but look at it another way. We're trying to find the total profit from x equals 0 to where profit is maximized. We're trying to find total profit. To find a total, you integrate a rate function. So to find total profit, we would integrate marginal profit. Well, marginal profit is nothing more than marginal revenue minus marginal cost. This is marginal revenue. This is marginal cost. Marginal revenue minus marginal cost is marginal profit. When you integrate that rate function called marginal profit, it gives you a total profit. So continuing like I have in this section, I would clean up my integrand And let's see, 1.7x minus 2.3x. Oh, I'm sorry. I left out my negative sign here. I was so excited. Negative 1.7x minus 2.3x. That's a negative 4x. 130 minus 14. It's 116. Get your antiderivative. So it's a negative 2x squared plus 116x. Evaluate that from 0 to 29 using the fundamental theorem of calculus, and you're going to get 1682. So this means the total profit from, I think it was mint T, so from 0 to 2,900 boxes of this mocha mint tea, I think. You know, where's the 2,900 come from? Well, look again at the example. Look at the words in the example. In the example, you were told X. X is the number of boxes of this mocha mint tea in hundreds. So this 29, that's representing 2,900 boxes. So the total profit from 0 to 2,900 boxes is $1,682. So to make sure you understand this, because this is I think it's a pretty cool, powerful application of integrating rate functions, knowing some stuff about profit, revenue, cost, marginal profit, marginal revenue, marginal cost. I'd like you to now try in section 7.2, try number 52. So you know the drill, pause the video, do number 52, then restart the video, and I'll be here at the board working it out. All right, number 52, you were given a marginal revenue function, a marginal cost function, and you were asked to find the total profit from selling 10 to 30 units. So you're integrating from 10 to 30, marginal profit. That's a rate function. Integrating a rate function gives you a total. So you're integrating from 10 to 30, marginal profit. Marginal profit is 216 minus 0.24x squared minus 20. Marginal profit is marginal revenue minus marginal cost. And I'd clean this up just a little bit. Let's see, 216 minus 20, that's 196. So to 196, I said. Get an antiderivative. So it's negative 0.24 over 3 x cubed plus 196x. Evaluate that from 10 to 30. If you want, you could do negative 0.24 divided by 3. It's a clean number. It's just negative 0.08. You don't have to do this, but either way, you use your fundamental theorem of calculus, and you're going to get $1,840 as being the total profit. So that's it here at section 7.2. Do the section 7.2, do all the exercises that I've listed for you to do. It's dreadfully important to do these because section 7.3 is just more area between curves. Two specific economic applications of area between two curves. Producer surplus and consumer surplus. So that's it for section 7.2. Do the homework. Thanks for watching.